Hi students, welcome in chemistry classes. I am Priyanka Jain and you are watching the videos of thermodynamics. Here we have started from the basic level and we are going toward the advanced level. Okay, all the topics I have tried to clear you. In our last lecture, we have studied about entropy. What is entropy? Okay, and what is Clausius inequality? Okay, now the basic problem is that you all does not know that which formula you have to use for the entropy. Okay, you have given the question in the question paper, but you cannot find out which formula you have to use. Okay, so I am giving you here the important formulas of the entropy, and then I will tell you where you have used which formula. Okay, so see here, first formula is for the entropy change, heating of solids and liquids. And one thing you have to remember here, that this formula is for without phase transformation. It means when there is no phase transformation, it means phase is not changing. If there is given water, then it is water. Okay, it is not changing to vapor. So here, see here, what formula you have to use? ds is equal to integration of dq reversible upon t. This formula you use. Okay, now you can write here dq, you know, is equal to n cm dt. This we have seen in our lecture of heat. Okay, so right here in this manner. Okay, now integration of ds will be equal to c here. If this n cm, this n is the number of moles, it is constant. If cm is constant, it means it is independent of temperature. Then we can take it outside. Okay, so it will go here. N cm T2 to T1 dt by T. Okay, and then we can write it NCM natural log of T2 upon T1. Okay, or you can write 2.303 NCM log T2 upon T1. Okay, so this is one of the formula. Okay, this is the value of del S. Okay, so write down this formula. Del S is equal to 2.303 NCM log T2 upon T1. And where you will use this formula? This formula you have to use whenever you have given the heating of solid and liquids and when there is no phase transformation. Okay. Now see the second formula for the entropy change for real gases. If we have taken real gas, okay, and when we have given a general process, any process is happening in a general way, okay, in a general process, then again we will write ds is equal to, we know, dq reversible upon t. This is the basic formula that you have to use. Now from the first law of thermodynamics, we know dq plus dw is equal to du. Okay, then dq will be equal to du minus dw. Okay, so dq reversible will be equal to du minus dw will be minus pdv. Okay, we can write it. So this will be equal to du plus pdv. Now we will put this value here. Okay, so we are getting ds is equal to du plus pdv upon t. Okay, now do its integration. So ds will be equal to integration of du by t plus integration of p dv by t. Okay, so what we are getting? So this will remain in this manner. Okay, this is the formula for entropy change of the real gas. Now for the van der Waals gas. When you have given van der Waals gas, then how you can change this formula? See here. See here, del u we know is equal to integration of n cvm dt plus pi t dv. Okay, this pi t is internal pressure. Okay, and we know pi t is equal to an square upon b square. This we have seen in our video of the enthalpy. If you have not seen the videos, you can find the links in the description box. Okay. So now what you have to do, del S is equal to, we know, du upon t. This is written here. Okay, this equation we have to use, plus p, we can write p dv upon t. Okay, now we have to put just the value of this del u. Okay, so what we are getting, integration of n cvm dt by t plus integration of an square upon v square dv by t, okay, plus integration of p dv by t. Okay, so this will be the formula for the van der Waals gas, but generally you have not asked about the van der Waals gas, so I think you can skip this formula. Okay, the next formula is for the entropy change for real gas in isobaric heating. It means if heating is done at the constant pressure. So ds will be equal to dq reversible. See here, this is the basic formula and we are deriving all the formulas from this one. Okay, so this is equal to integration of n cpm dt upon t. So ds will be equal to n cpm natural log of T2 upon T1. Okay. So this is the formula when you have given the isobaric process. It means when the pressure is constant. Now suppose you have given isochoric process. Okay. It means entropy change for real gas. We are seeing for real gases. For real gas in isochoric process. Then what will happen? Here just only you have to change Cp to Cv and Cvm. Okay, molar heat capacity at constant volume you have to use. So natural log of T2 upon T1. This will be your formula. In more general cases, you have asked about the entropy for the ideal gases. Generally, you have given ideal gases. Sometimes you have given the real gases. So you will have to identify in the question paper which you have asked. Which thing you have asked. Okay, if you have given the ideal gas or you have given the real gas, then you have to see the process. Which process is happening? Isochoric, isobaric, okay, whatever, isothermal, whatever thing do you have given, you have to use here. So next thing is the entropy change for ideal gas. We are firstly seeing a general process. Okay, just you have given that the gas is ideal and you have to find out the entropy change. So what you will do, see here, ds is equal to dq reversible upon t. This you know. Okay, now this will be equal to du minus dw upon t. Okay, and we can write it du plus pdv upon t. We can write. Okay, now see here, put here integration term. Okay, for ideal gas, if you have given ideal gas, you know that du is equal to n cvm dt. This you know, I have told you in my video of the internal energy. Okay, and one more thing, you know that PV is equal to nRT. These two things are true for the ideal gases. Okay, so just you have to remember this one. So del S will be equal to integration of du upon t plus integration of pdv upon t. Just we have separated the terms. Okay, now del S will be equal to, put here the values. Okay, and cvm dt by t. Here you have to put the limits t2 to t1 plus nRT integration of nRT upon v dv upon v. Okay, and here you have to set the limits v2 to v1. So what you are getting? You are getting del S is equal to n cvm ln t2 upon t1 plus nr natural log of V2 upon V1. This one is the most important formula. Okay, in general cases, whenever you have given nothing, you have to find out the entropy change, or you have given the ideal gas, or you have given a general process, then you have to use this formula. Okay. Okay, now see the conditions. In this case, in ideal gas, you have seen the conditions. First condition you have given that the entropy change for ideal gas in isothermal process. For isothermal process, we know that dt is equal to 0. This is true for the isothermal process. Okay. And we know that for the ideal gas, the general formula for the entropy change is NCBM, natural log of T2 upon T1, plus NR, natural log of V2 upon V1. This we have seen. Okay. Now, we know NCBM, natural log of T2 upon T1, will be equal to 0 for the isothermal process. Okay. And P1 V1 is equal to P2 V2 for ideal gas. Okay. So we can write V2 upon V1 will be equal to P1 upon P2. Okay. So what we are getting? First thing that we are getting that del S is equal to NR natural log of V2 upon V1. Okay. Or we can write del S is equal to NR natural log of P1 upon P2. So these are the two formulas. One formula is this one and the second formula is this one. Okay. So if you have given the final and the initial volume, then you will use this formula. Okay. And if you have given the initial and the final pressures, then you will use this formula. Both the formulas are applicable for the isothermal process for the ideal gases. Okay. This is the first condition. Now see the second condition. Suppose you have given the adiabatic process. It means entropy change for ideal gas in adiabatic process. Okay, now the process is adiabatic. Okay, first of all, there may be two conditions. One is reversible process. In reversible process, first of all, you should know that for the adiabatic process, Q reversible will be equal to 0. Okay, and del S of system we know is equal to Q reversible upon T. This we know. Okay. So del S of system will be equal to 0 because our Q reversible is equal to 0. Okay. Now del S of surrounding. Del S of surrounding is equal to Q of surrounding divided by T, and this will be equal to 0. Okay. So we can say del S of surrounding will also be equal to 0 for the reversible process. Now, if you have given the irreversible process, for irreversible process, in this case, Q irreversible of the system will be equal to 0. Okay. And Q irreversible of the surrounding will also be equal to 0. And del S system, we know del S system is equal to Q reversible by T. It is not equal to Q irreversible by T. Always remember that whenever you have given the entropy, then it is equal to Q reversible by T. It is not equal to Q irreversible by T. So, it will not be equal to 0. Okay. So, we can write del S system will be equal to NCBM natural log of T2 upon T1 plus NR natural log of V2 upon V1. But del S surrounding will be equal to 0. Okay. And we know del S total is equal to del S of system. Because the del S of the surrounding is equal to 0. This is equal to 0. So del S total will be equal to del S of system. This is the case for the adiabatic irreversible process. Now, one more important thing is the entropy change for phase transformation. Till here we have seen the things all that are for the non-phase transformation process, that are without phase transformation. But now we have to see the entropy change for phase transformation. Suppose a liquid A is changing to the solid B. Okay, this is solid state. Okay, the phase transformation occurs at constant pressure and temperature. Okay, this occurs at constant pressure and constant temperature. So dP will be equal to 0. Okay, and dt is also equal to 0. So C will be equal to Cpm. If phase transformation occurs at the melting point or boiling point or at the sublimation point, then means it is reversible process. Okay, so del S will be equal to Q reversible by T, and this will be equal to del H upon T. Okay, if del S, we have given the del S for the vaporization process. Suppose we are seeing the entropy change for the vaporization process, then this will be equal to del H of vaporization divided by TB. It means boiling point. Okay, this is one formula. If we have given del S fusion, then it will be equal to del H of fusion divided by Tm. It means melting point. This is the another formula. And del S of sublimation will be equal to del H of sublimation divided by T of sublimation. Okay, so this is the third formula. Alright, so these are the three formulas when you have given the phase transformation. It means suppose you have given a liquid is changing to solid, or solid is changing to liquid, or liquid is changing to vapor. Anything you have given in which the phase is changing. Okay, so always remember in that case you will have to use these three formulas. Okay, or in other cases you will have to use the formulas that I have given you previously. Okay, so these are the full details of the formulas, all the formulas that you will need for the entropy change. No other formula you needed. Okay, so if you want, you can take its PDF. I have given the link of the PDF in my description box. Okay, all the videos, link of PDF I have given in the description box. So from where you can write down the formulas. Okay, and if you are liking my videos, please comment me and please share the videos. Please subscribe the channel. Thank you.